anytime you're about to do something with a pointer, check if it's in fact null. And the reason is strcomp is actually a pretty simple function. It does what we did last week. It starts at the left of each string and compares. But it does not check if a pointer is bogus or if it's 0. So the problem is if you accidentally somehow make S1 or S2 null, for instance, the computer's running low on memory, or you've initialized them to null yourself, any number of ways, we'll see more over time, and you accidentally pass null pointers to strcomp, it probably will crash on you. So in short, always check the values of pointers. All right, so we saw one more sophisticated example, namely trying to copy strings. And our first attempt at this also was flawed. So this was copy1.c last week. Recall that I typed in a word, I think hello, then to, and I tried to capitalize it by just changing the first letter of the word. But every time I tried to capitalize that word hello, I ended up changing both copies, the original and the copy. Because how did I try to copy these strings last week? Well, I used this line, S2 gets S1. And really, I can simplify that. And you might have tried this in previous problem sets. This even looks more convincing. This looks perfectly legit. String S2 gets equal to S1. But it's not right. Because what is really happening in this one line of code? Sorry? Exactly. So you are creating a new pointer, but you're not creating a new string. If we define a string as a bunch of contiguous characters, all we're defining with char s2, char star s2, is another pointer. What are you pointing at? Well, you are pointing at whatever the user typed in. So if this is s1, this is s2, and the user typed hello, and that word is over here in RAM, at this point in the story, they're both pointing to the same place. All you've done is create a new pointer, not a whole array of characters. So we did solve this, and we introduced, finally, copy2.c. So in copy2, it was admittedly a little more complex, but if you think about what each step is doing, it actually solves the problem quite nicely. So the left-hand side stays the same, char star s2. And again, if this is starting to intimidate, it's again just string s2. But you have to start remembering now that strings involve pointers. So what now am I storing inside of s2? Well, I claim I'm putting in S2 this time the address of a new chunk of memory. That memory initially has just junk in it. Who knows what's in there? But how much memory have I just allocated? Well, malloc is memory alloc. And it takes an argument, and that's a number, an integer. And that integer is how many bytes do you want. So if I typed in HELLO, I want 5 bytes for malloc. OK, I actually want 6, the sixth one being for the \0. So I always want a +1. So I get the string length of S1 plus 1. And then just because I've kind of done this before and I know these kinds of crazy corner cases that can arise, why did we say last week that I then want to multiply that number by the size of a char? Yeah.
Because different languages use different memory sizes?
Exactly. And let me tweak slightly. It could be different machines use different sizes for chars. So in a typical system, certainly the appliance and most of the computers you all own, typically a char would just be 1 byte or 8 bits. But just in case we hand this code off to a fancier computer, or it lingers around for 10 years and the next computer actually uses 2 bytes for every char, this way we're being a little defensive and the program will keep working. And silly though this example is, think about, again, the Y2K issue, right? It was this mentality typically of either, memory is expensive, we need to shave off every byte we can and just use 2 digits, or it was a brash mentality like, who the heck is going to be running our code in 30 years? Well, a lot of people were still running the code. So it's this kind of mentality, trying to make sure that your code is future-proofed and always correct, that is a very good habit to get into. So what is malloc actually doing? Well, it turns out that malloc, memory alloc, is not taking memory from anywhere you see here on the screen. Because recall that the stack, these frames that we keep drawing as slivers on this rectangle, they go away pretty quickly, right? As soon as a function returns, that's it. That memory is no longer safe to use. So this feels problematic. If malloc actually borrowed RAM from this part of the picture, well, as soon as the swap function returned or some other function returned, even if it had asked malloc, give me some memory. How much memory? Well, whatever number you passed in as an argument. What if then someone else needs that memory? So in other words, when you call malloc, you want to allocate memory permanently, or at least until you are ready to give it back. The stack is very ephemeral. Anything on the stack can go away at any time as soon as these functions return. If you want to allocate a chunk of memory for like a word like hello, and you want that memory to stay active even after your functions themselves have returned, you actually need to put it elsewhere. So we drew briefly in previous weeks this picture here. This whole rectangle now might represent your computer's RAM. At the bottom of this is the stack. There's also this other stuff that are generally called environment variables. These are special things like your username. So it turns out that when you run a program, the word jharvard is actually put in RAM. And that is accessible to you, the programmer. We typically don't need it or use it, but there's stuff like that that's put below your stack so that it's there for main and anyone else who wants it. At the very, very top of your RAM is the so-called text segment. And what does text mean? So it's a little misleading, but for historical reasons, text segment is the zeros and ones that you wrote by way of compiling your code with GCC. So the text segment is literally the zeros and ones that compose your program, Sudoku or Game of 15, anything like that. They're loaded into RAM, and that should just make intuitive sense, right? If you double-click an icon or run a program's name, for anything to happen, those bits need to be loaded somewhere so the computer can start doing something with them, and indeed they're loaded into RAM in this way. Now lastly, there's a couple other things that are put way up there. Initialized data and uninitialized data. There's some subtleties there, but in a nutshell, on the rare occasions when we've used global variables, for instance, the Game of 15, we had G, which was the global board at the very top of the file. Global variables go there too. And that should also now make intuitive sense because you don't want your global variables on the stack because then they might disappear mid-execution of program. But if they're way at the top, they're going to stay there, is the takeaway here. So that leaves just one last segment. So this was someone's bright idea, but why not have this thing called the stack grow up, 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 up? And we need some other space, so let's have this other space grow down, 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 down. Now, of course, this is like a problem waiting to happen, and we've induced this problem before, right? When I wrote that silly function called foo, and then I had foo called foo, and I didn't have any kind of base case or if condition to stop foo from calling itself, what happened? Well, the stack went up, 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 up. It clobbered the so-called heap, even though we didn't call it that day, and the program terminated. The operating system said, segmentation fault, you have exceeded your segment. But this is kind of nice, right? This might seem kind of stupid in that this is like, two trains on a track. This is not going to end well. But if you think about it, in the real world with your computer, you only have a finite amount of memory. So it's not as though we could just flip this picture around and just say, let the memory grow up for both of these sections of memory, both heap and stack. Right? Eventually, you're just going to hit your 2 billionth byte of RAM, or however much you have. So this is actually nice in that it lets us use the whole potential memory. And bad things only happen if we get greedy and we try to load in too big of a data set. We call a function too many times. But long story short, malloc puts memory on the heap. And it puts it way up there away from the stack. And again, if this is 2 gigabytes, it actually takes a bit of effort or a bit of stupidity to actually have the stack hit the heap, though it does sometimes happen. So let's take a look. Let me go ahead now and open up a little file called bar.c, which actually does not do anything that's useful, but it does now play with a bunch of these various syntactic details. So if at any point something goes over your head, just look confused, raise your hand, because all of these are just now re-emphasis on these same basic building blocks. So this is bar.c. At the top, these two things are called quick quiz. So prototypes, right? So apparently there's two functions, foo and bar, defined elsewhere in this file. I'm just informing GCC that they're going to exist at some point. So here's main. So this, in English, if you were asked, what is this doing? Declare an integer called a. What does that really mean? Allocate 32 bits and call it a. Where are those bits stored, though? Where is a in this picture? So it would be in the stack. This is a local variable. Local variables have been and remain on the stack. The only time something is going to end up on the heap is if you explicitly call malloc. That is a safe rule of thumb. Now, how about here? As an aside, too, you might see differences between me and the TFs or even textbooks. This is probably the best habit to get into, whereby the star is immediately next to the variable name, only because it can be confusing if you have multiple variables declared on the same line. So in short, this is probably the best style to get into. But char star s means give me a pointer to a character. More technically, give me 32 bits in which I can store what? Not a char, but the address of a character. So char star s means give me 32 bits that are going to store an address. The address of what? The address of some char. All right, so on the right-hand side, we now have hello world. Now, this is hard-coded, right? This is not a variable. I'm not using getString. So just as an aside, where is hello world stored? This is effectively global data. So when I said before global variables are way at the top, so is a hard-coded string like hello also put way up there. All right, so what else here do we have? We have printf, %s, \n. Now this looks a little scary. So what is s? Well, first let me delete the scary part. So we just have s bracket 0. If I print out s bracket 0 and then put %c here, that prints a char. What char does it print? 0, 1, 3, 4, 5, 6. So I just figured it out too, right? W. If I counted right? 0, 1, 2, 3, 4, 5, 6, 7. So the 7th character, 0 indexed, is W. But if I instead say, I don't want to print a char, I want to print a string, so I change the %c to %s. And I don't want to print s bracket 7 because that's actually the 7th character, 0 indexed. What does the ampersand operator do in this context? What am I getting the address of, to be clear? The address of? I'm getting the address of the 7th character. So that's kind of interesting. Now, that doesn't feel like a complete string. In fact, that's smack dab in the middle of this bigger string. But guess what? What does the word world also coincidentally end in? The null terminator, right? That substring world also obviously ends in the same \0. So ampersand s means get me the address of the 7th character. Well, what is that? Well, if we're all in agreement that W is it, that's where we are in the story. But when you say ampersand s bracket 7, that means, OK, I don't want W. I want the address of W. So that means now somewhere, and we don't need to project this. It's just going to be a silly rectangle. But that means somewhere is the word H-E-L-L. OK, now it's enough words to project. Let's try our fancy new technology. That's how bad my handwriting looks for those who've never seen it. All right, so we have W-O-R-L-D \0. And now if I break this up into something that looks a bit more like an array. OK, normally this would be a much prettier picture. But maybe this is not the best use of technology. OK, that's the projector doing that. So when we say s, what is s? S is the address of the start of the string itself. And it ends back here at the \0. But if I say s bracket 0, that takes me to the 7th character, 0 index, and that's literally W. But if I say what's the address of it, that's like asking the question, what is the address of this particular point in this whole array that we think of as a string? Well, who knows what it is? It's like 0x 1, 2, 3, 4, 5. But if I then say print the string that starts at that address, what does printf do? Well, it's a pretty simple function. It starts here, and it prints, and it only stops when it sees \0. So what word is going to get printed based on this second line of code in main? World. Now, again, highlighting it now clearly doesn't work, just as I highlighted it. So this is kind of a silly exercise here. But again, it just means that all of this stuff with pointers and ampersands and stars just reduces still to these basics. So let's do this now. A gets 5. So what is A? What data type? All right, so it's an int. We declared that a couple lines before. A gets 5, puts the number 5 in A. So that's kind of old school. Foo A. I don't know what foo is going to do, so let's scroll down now. So foo takes in an argument, and that argument is of type int. So at this point in the story, what value is in n? So 5. But think back to the picture. This actually looks a little different. So if this is now my picture, we're talking about foo now, not swap. But whereas A exists in main's local frame, the second rectangle here, if we call that foo, so actually, we have a computer here. Foo's locals, foo's parameters. So where is actually this number n stored? Well, it's going to be stored in the thing called foo's parameters. So they're distinct copies. And we can see that now with this.